Hello, I am A/P Dr. Woon Kai Lin from the Department of Physics at the University of Malaya. In this video, we will explore the question, how does quantum physics affect our everyday life? We will be comparing classical intuition with quantum reality, looking at the rules governing the universe and what happens when they break down at the quantum level. The golden rule of classical physics is the conservation of energy. Energy cannot be created nor destroyed, only transformed or transferred. This means the total energy of an isolated system remains constant over time. These deterministic rules govern the universe at a large scale. Whether it's a ball rolling in a valley or a satellite orbiting Earth, the underlying math involving the conservation of energy is the same. When we translate conservation of energy into the quantum realm, we use the Schrödinger equation. This equation expresses the total energy of a particle through kinetic and potential energy components. The ultimate question in quantum physics is an electron a particle or a wave? Based on classical intuition, if electrons are physical particles, shooting them through a double-slit partition should result in two distinct bands on the screen. However, electrons defy classical expectations. Instead of two bands, they create an interference pattern, suggesting that a single electron can pass through both slits at the same time. The electron is both a wave and a particle. Remarkably, even when single particles are fired one by one, they gradually build a predictable, continuous wave pattern over time, demonstrating their wave nature. This wave nature is not limited to subatomic particles. Complex biomolecules, like the polypeptide gramicidin A1, also exhibit matter-wave interference, showing the wave nature of matter at a larger scale. We map the unseen quantum world using probability. The square modulus of the wave function is the probability density that a particle is at a specific location. Traveling wave packets illustrate a trade-off. Higher localization pinpoints position but obscures momentum. This trade-off is formalized by the quantum uncertainty principle. It sets a fundamental limit on precision, stating that the universe inherently blurs the exact position and momentum of matter simultaneously. A particle exists in a superposition state, meaning it can be in multiple states simultaneously. For the double-slit experiment, an electron exists in a superposition of passing through both slits until it is observed. Scaling probability to the macroscopic world is evident in the decay of radioactive nuclei, which is a strictly random process governed by its half-life. For example, plutonium-240 has a 50% decay probability after 6,560 years. Schrödinger's cat illustrates the box of overlapping realities. Since the decay of the atom is probabilistic, until the box is opened and observed, the cat exists in a mathematical superposition, simultaneously alive and dead. A core mystery of quantum physics is that the act of looking changes everything. If we place a detector to observe which specific slit the single electron goes through, what happens to the wave pattern? The mere act of observation forces the electron to choose a path, collapsing its wave nature entirely. By measuring the quantum realm, we force it back into the classical rules of particles. The observer is intrinsically linked to the fabric of reality. This video explores quantum colors, showing how subatomic physics paints the foods we eat. Specific frequencies of reflected light create the visible colors we perceive. Subatomic energy transitions are what dictate light absorption. In the classical world, objects exist in one valid state at a time. For example, an elephant is either gray or multicolored. However, in the quantum realm, a particle can exist in a superposition of multiple states at once, meaning it can be gray and multicolored. Quantum particles are delocalized, meaning they lack a single specified position. While a classical particle has an exact position, a quantum particle's location is described by a probability function, indicating it is somewhere around a certain region with high probability. Nature loves symmetries, and matter behaves exactly like light. Both the photon and the electron possess a dual character, acting as both a wave and a corpuscle. The electron forms a standing wave around the nucleus. When confined, waves can only exist in perfect harmonics. Because the boundaries are fixed, only specific wavelengths can fit perfectly, creating discrete harmonics like the first, second, third, and fourth harmonics shown here. In three-dimensional space, confined electron waves create complex geometric clouds known as orbitals. These shapes, such as s orbitals, spherical, and p orbitals, dumbbell, are not physical paths but represent where an electron is most likely to be found. Confining the wave into a potential well shows that the width of the box dictates which wavelengths can fit inside. Higher energy levels pack more waves into the exact same space. Because only certain waves fit, energy levels are strictly discrete. Electrons jump between precise energy levels, and each specific jump corresponds to a distinct wavelength, which, in turn, corresponds to a distinct color of light. Conjugated molecules act as physical quantum boxes. The electrons within these systems are delocalized, meaning they are free to move back and forth, trapped only by the length of the molecular chain. The equation of reality for these quantum boxes is that size dictates color. The length of the molecular box L determines the energy gap E, which then dictates the frequency or color of light absorbed. A longer molecule means a smaller energy gap. In the case of a caret, $beta $carotene contains delocalized electrons in a relatively long box. The energy jump from the highest occupied state to the lowest unoccupied state perfectly matches the energy of blue light. By absorbing blue light, the remaining light appears bright orange. The cranberry juice effect demonstrates shape-shifting quantum boxes. Changing the acidity, or pH, physically alters the structure of the pigment molecule, and a structural change means a change in our quantum box's length, L. Shrinking the box shifts the color spectrum. The conjugation length at high acidity is greater than at low acidity. When L shrinks, the energy gap changes, and the absorption peak drops, shifting the juice from a deep, bright red to a washed-out pale red. Color is a biological imperative, not just an accident of physics. Colorful fruits and vegetables are packed with polyphenols, molecules that have perfectly evolved to utilize this exact quantum effect. They are visually appealing and vital to consume. Grape skin polyphenols, acting as an, quote, edible sunscreen, are the ultimate quantum shield. Their molecular box length is tuned to absorb high-energy, damaging UV radiation, protecting you from the inside out. Welcome to The Invisible Architect, a video exploring how the quantum realm shapes our reality. We'll look at quantum tunneling, wave interference, and the subatomic rules governing biology, chemistry, and modern technology. At the smallest scales, matter is described by wave functions, derived from the Schrödinger equation. These functions map where a particle is likely to be found, treating electrons not as solid dots, but as, quote, clouds of probability. In classical mechanics, an object needs sufficient energy to climb a hill. However, in the weirdness of quantum mechanics, a particle can tunnel straight through a potential barrier, keeping its total energy exactly the same. In chemical reactions, classical models require particles to overcome an activation energy. The quantum tunneling model allows low-mass particles, like protons and electrons, to pass through classically forbidden regions. Consider the case of hydroxymethylene. Attempts to detect it failed because it rapidly decayed into formaldehyde via quantum tunneling. This proves the phenomenon occurs even within the smallest water droplets. Quantum biology suggests that biochemical processes involving proton transfer are actively facilitated by quantum tunneling. Hydrogen, being the lightest element, has the highest probability for this tunneling to occur. The smoking gun proof involves deuterium, an isotope of hydrogen with twice the mass. The transfer rate for deuterium is significantly reduced, exactly matching quantum predictions, confirming the reliance on tunneling. Quantum tunneling can also cause genetic mutation. During DNA replication, a proton can tunnel across the double helix, creating a rare tautomeric form. This accumulation of mutations over time is hypothesized to drive biological aging. According to the de Broglie wavelength, quantum physics asserts that the electron is a wave. Because matter has a wave nature, particles can undergo reflection, constructive interference, and destructive interference. Nature actively uses optical wave interference. The brilliant blue of the morpho butterfly is not produced by pigment, but by physical nanostructures that cause reflection and interference of specific light waves. Inside any crystal, the positive nuclei of atoms create a highly regular, repeating electrical potential. This acts as a microscopic structural grid guiding electron waves through the material. As electron waves move through this regular potential, they reflect off the internal structures. For certain wavelengths, this reflection causes destructive interference, meaning they cannot propagate inside the crystal at all. This inability of certain electron waves to propagate through the atomic lattice creates a, quote, band gap. A band gap is a strictly forbidden energy zone, where electrons are physically disallowed from possessing energy levels due to wave interference. The size of these quantum band gaps dictates our modern world. Metals have overlapping bands allowing free flow, Semiconductors have a narrow gap, forming the basis of all computer chips. Insulators have a massive gap, preventing electron flow. Quantum mechanics governs our reality, from the tunneling protons driving biological aging to the wave interference that colors nature and powers our microchips. Quantum rules are truly the invisible architects of our macroscopic world. Google Maps and other navigation services rely not just on space technology, but on fundamental quantum technology. This video will explore the quantum receiver in your pocket. An invisible quantum web, governed by subatomic physics, dictates much of the modern world. We rely on quantum mechanics to navigate our classical world, from routing the internet to global military supremacy. Your smartphone acts as a quantum receiver. Accurate navigation depends on the speed of light. To track location precisely, time must be measured flawlessly. A tiny timing error can put you kilometers off course. GPS satellites use atomic precision to provide exact coordinates. Traditional clocks use physical objects like pendulums. Quantum clocks rely on the invisible heartbeat of an atom. They measure the exact frequency of light needed to make an electron jump between energy levels. This relies on the rule of quantization. Electrons in an atom only exist in specific, discrete energy states, meaning an electron cannot be, quote, halfway between these states. A quantum jump occurs when an electron changes energy states, requiring a photon with an exact, specific energy. This jump frequency is identical for every cesium atom in the universe due to fundamental physics. Inside a cesium clock, atoms are sprayed with microwaves. Scientists tune the microwave frequency until the electrons start jumping. That exact frequency is our perfectly stable pendulum, turning light into time. The ultimate definition of a second is based on the cesium atom. 1 second is defined as exactly 9,192,631,770 oscillations of the microwave radiation required for this specific electron jump. The GPS network is a constellation of satellites. Each GPS satellite carries multiple atomic clocks, constantly maintaining this 9 billion tick quantum heartbeat. This provides unmatched stability. Atomic clocks lose only 1 second every 300 million years. Advanced atomic clocks are now pushing boundaries by using superposition to increase measurement sensitivity. These atomic clocks serve as the metronome of the global economy. They stabilize power grids, route the internet, and timestamp financial transactions, where modern systems process 1 billion messages per second. Without the absolute predictability of quantum energy jumps, GPS would instantly drift. Within minutes, everyday navigation would become entirely useless. This exact atomic heartbeat synchronizes the entire global internet, secures international banking systems, and regulates worldwide power grids. It is life synchronized by atoms. We live our lives in a classical world, but we navigate it using the precision of the quantum world. This is the marriage of the macro and the micro. Welcome to this video, where we will be demystifying quantum entanglement, a concept often described as spooky action at a distance. Entanglement occurs when two or more particles become linked, losing their individual identities to form a single, unified quantum system. The result is that whatever happens to one particle instantly affects the other, regardless of the distance separating them. This bizarre reality even frustrated Albert Einstein, who skeptically coined the term spooky action at a distance. He was deeply unsettled by the idea of particles communicating or influencing each other instantaneously across space. To create entangled photons, scientists use a specialized laser and a nonlinear crystal. A high-energy photon is fired from the laser, aimed precisely at the crystal's atomic structure. Occasionally, the high-energy photon splits into two lower-energy photons. Due to the conservation of energy and momentum, these, quote, twin photons are born perfectly entangled. For example, if one has horizontal polarization, its twin is forced to have a vertical polarization. Until they are measured, entangled particles exist in a superposition, a blurry mix of all possible states simultaneously. Like the theoretical quantum elephant that is both gray and multicolored, neither photon has a definite state yet. We can test this cosmic connection by sending one photon, photon A, to a lunar outpost while keeping photon B on Earth. Both remain in their blurry, undecided superposition until a measurement is made. Measuring one photon instantly causes a wave collapse in its twin. The moment photon A is measured to be in a horizontal state, photon B on Earth instantly collapses into the complementary vertical state, with zero time delay, bypassing the speed of light. However, this instant correlation does not enable faster-than-light communication. While the link is instantaneous, the outcome of the measurement is entirely random, meaning you cannot control the state of photon A to send a deliberate message. The unbreakable randomness of quantum physics protects the laws of relativity. Because the wave collapse cannot be controlled, no structured information can be transmitted faster than light, ensuring the cosmic speed limit remains safe. Quantum entanglement is not just a theoretical concept. Nature already uses a version of this spooky action in avian biology, where birds utilize this quantum phenomenon within their magnetoreceptor cells to navigate the globe. Finally, entanglement guarantees an absolutely unhackable quantum internet. Any attempt to spy on the connection by measuring an entangled photon will permanently break the link, instantly destroying the data and setting off an alarm. This video explores the paradox of X-ray ghost imaging, focusing on decoupling resolution from radiation exposure to capture perfect diagnostics with microscopic risk. Traditional X-rays use a brute force approach, known as the straight-through current paradigm, where a dense beam of photons passes through the subject to a sensor. This quest for high resolution has a high biological cost due to ionizing radiation. X-rays carry enough energy to damage DNA and increase cancer risks by knocking electrons out of atoms. X-ray ghost imaging is a complete departure from straight-line photon exposure. It adapts visible light techniques to the X-ray spectrum to decouple image resolution from patient exposure. Step 1 is the split, where a specialized crystal beam splitter separates a primary X-ray into two identical correlated beams, both sharing a highly specific, random speckle pattern. Step 2 is the patient path, or path A, where an extremely weak X-ray beam is directed at the patient or biological sample, ensuring minimal radiation exposure. A bucket detector is positioned behind the patient. This single pixel detector cannot form an image. Its only function is to count the total amount of light or faint flashes that pass through the body. Step 3 is the camera path, or path B. The second, identical beam is routed away from the patient and shines directly onto a high-resolution, multi-pixel digital camera to capture high-resolution data without patient exposure. The system operates with two correlated paths simultaneously: Path A, with low data and low exposure for the patient, and Path B, with high data and zero exposure for the camera. Step 4 is the computational ghost. The bucket detector registers a drop in intensity as X-rays hit dense tissue. A computer then records the exact speckle pattern hitting the high-res camera at that precise microsecond. By correlating thousands of these flashes, the computer mathematically builds the patient's internal image. The final, high-resolution ghost image is constructed exclusively from the data of the second beam that never touched the patient. The process is low dose because the bucket detector doesn't need to resolve an image. It only needs to detect faint flashes of total intensity, allowing the patient beam to be incredibly weak. Advanced algorithms, referred to as the software multiplier, supercharge the physical setup. Compressed sensing and deep learning enable perfect image reconstruction from a microscopic fraction of raw data. This technique allows for perfect image reconstruction using less than 25% of the X-ray photons used in a traditional CT scan or X-ray. X-ray ghost imaging offers maximum resolution with microscopic radiation, drastically reducing the risk of cellular damage. The future of medical imaging relies on computation, not brute force exposure. Welcome to this video on quantum nature, the hidden physics shaping biology, climate, and birds navigate vast distances using a built-in sense of the planet's magnetic field. Their migration behavior changes demonstrably when the surrounding magnetic field is altered. This video will explore how they find true north without a compass. There are two main competing theories for the biological compass. One involves tiny iron particles. The stronger hypothesis, however, is the quantum chemistry sensor, which relies on a quantum trick. The sensor is a light-sensitive protein called cryptochrome, located in the retina. This specific sensor only activates in the presence of light, explaining why the avian compass depends on specific colors of ambient light to function. Ambient light acts as the trigger for a tiny chemical event. Light hits the protein, causing an electron to shift. This process creates two linked electrons. These two linked electrons form a, quote, radical pair. They function as a highly sensitive magnetic probe and operate in two distinct teamwork modes based on how their spins align. Earth's magnetic field doesn't rigidly force the electrons into a specific state. Instead, tiny energy differences simply tilt the probability of which mode A or B wins. It's a quantum coin flip influenced by the magnetic field. These two chemical modes produce entirely different nerve signals. The resulting mix of chemical products dictates how the optic nerve cells respond, translating quantum states into biological data. The bird perceives this information as a shifting magnetic overlay on its visual field. Evidence suggests the bird sees a visual pattern indicating direction, rather than feeling a physical pull. Nature utilizes quantum physics at tiny scales to navigate the globe. A microscopic quantum chemistry effect scales up from a photon hitting cryptochrome to a magnetic tilt to become an incredibly reliable compass cue for global migration. Photosynthesis is not 99% efficient at turning sunlight into mass. However, the internal transfer of captured light energy is near perfect. We are zooming into the first few trillionths of a second to see how captured energy is delivered. The biological challenge is delivering the captured energy before it disappears. If the delivery is too slow, energy leaks away as useless heat or light. The trick is getting the energy from the antenna to the reaction center extremely fast. Light energy moves through a leaf as a roaming excitation, not as a tiny marble. After absorption, the energy behaves less like a physical object and more like a spread-out ripple or a shared excitement across molecules. Classical physics assumed the energy randomly hopped from molecule to molecule. However, randomly hopping between molecules wastes time and bleeds energy. This drunk walking takes too long, and energy would leak out before reaching its destination. Quantum wave exploration allows the energy to test many routes simultaneously. This is the quantum upgrade. This natural wave behavior operates at incredibly small scales, allowing parallel route testing to find the fastest way. Think of this wave exploration like sound echoing through a room to find an open door. Waves naturally find efficient routes. They don't choose a single path. Interference amplifies good routes and cancels out bad ones. A tiny bit of molecular jiggle is the secret to keeping the energy moving. The biological system finds a perfect sweet spot. It balances order for wave-like exploration with enough noise from heat vibrations to avoid getting trapped in dead ends. Quantum coherence is the ripple staying organized long enough to matter. It's the state where the ripple remains unified and wave-like. In photosynthesis, this coherence is ultra-fast, improving routing before fading into random movement. In the microscopic world, sheer speed beats energy loss. Faster delivery means fewer chances to lose the captured energy. The advantage of quantum routing is getting to the destination before the energy dissipates. Lightning-fast delivery triggers a one-way chemical step to secure the energy. Once delivered, the reaction center converts the fleeting light energy into a stable chemical form through charge separation, which acts as a one-way door. While the microscopic transport is near perfect, the entire plant is not 100% efficient. Biology has many unavoidable loss channels, like reflected light, heat, and plant respiration. The overall sunlight to biomass conversion remains much lower. Nature's ultimate trick combines wave exploration with helpful noise for rapid delivery. Photosynthesis utilizes a brief quantum wave-like surge, assisted by molecular vibrations, to deliver light energy with near-perfect efficiency before it fades away. This concept illustrates the quantum weirdness of exploring every path simultaneously. Classically, a particle takes a single path. Quantum mechanics, governed by the Schrödinger equation, dictates a non-zero probability for a particle to take any path, searching the entire maze at once. Humanity's attempt to technologically mimic this efficiency is seen in quantum computers. These devices use superposition and entanglement to explore all possible solutions simultaneously, finding the optimal answer. Much like a plant processes sunlight, atoms behave as quantum springs, seeking minimum energy. Molecules oscillate around an equilibrium position. Kinetic energy trades with potential energy as the molecular bond stretches and compresses, always seeking the most stable, minimum energy state. These precise molecular vibrations are what trap heat. Knowing the minimum energy configuration allows us to map exactly how these molecular springs behave when hit by radiation, such as the asymmetric stretch vibration in CO2 that is IR active. The atmospheric window is the specific range of wavelengths where energy escapes back into space. Water vapor absorbs vast amounts of infrared energy, yet CO2's absorption spectrum is particularly significant within this critical window. Water vapor provides our baseline habitable temperature. However, CO2's specific quantum vibrations absorb energy exactly within the atmospheric window that water leaves open. Adding CO2 forces the system out of its delicate natural equilibrium. The harsh mathematics of the carbon budget shows a mean budget of around 600 gigatons of CO2 left to emit before warming exceeds 1.5 to 2 degrees Celsius. Peaking now gives us the most time to reach net zero emissions. We cannot negotiate with the fundamental laws of physics. To ignore the carbon budget is to attempt to violate fundamental quantum mechanics. This highlights the intersection of politics and science in addressing climate change. In artificial intelligence, training a deep neural network requires finding the lowest possible error rate, the minimum energy state, in complex parameter spaces. Current algorithms blindly navigate these steep valleys to find an optimal solution. Nature is the ultimate optimization engine. The future of human innovation, from mitigating climate change to training advanced AI, lies in mimicking the quantum efficiency of a simple leaf, exploring all paths at once to synthesize efficient search strategies. Welcome to this video on physical AI and the quantum frontier. We will explore the convergence of advanced robotics and quantum materials science, integrating mechanical systems with atomic scale precision. Generative physical AI enables autonomous systems to perceive, understand, and perform complex actions in the physical world. It translates generated insights directly into physical actions. A major challenge in traditional AI is the data bottleneck. Training systems to understand physical environments requires massive, inefficient datasets, often exceeding 10 million data points, just for basic interactions. Physics-informed neural networks, or PINNs, address this by mathematically embedding the known laws of the universe directly into the software architecture. This approach can cut the required data by 2 to 3 orders of magnitude. The PIN architecture contrasts with standard neural networks, which treat the world as a blank slate. PINNs hard-code reality by baking in physical properties and minimizing deviations from known physical laws like energy conservation. This efficiency funnel illustrates how injecting physical laws, such as Maxwell equations, reduces the data required from over 10 million to as low as 10,000 data points for noise-free, simple algebraic results. The next evolution is quantum-aware AI. This is AI that is learned and executed on hardware that adheres to the same quantum rules governing the materials themselves. There are 2 main approaches to quantum integration. First principles quantum runs algorithms on today's hardware, but mathematically knows the rules of the Schrödinger equation. Intrinsic hardware embeds physics via the atoms themselves. Quantum hardware is moving from simulating physics on silicon to computing directly with atoms. An example of this is a neutral atom Hubbard quantum simulator, as published in Nature. The ultimate goal is to move from atoms to life. Mastering the lowest level of physical reality, like quantum mechanics, unlocks the capacity to simulate and master the highest, including biological complexity and intelligence.